So it is a great pleasure for me to give a talk here. I decided to give an unusual kind of talk where you don't talk about something which already happened and is known, but you try to talk about something which hasn't happened and is not known, especially to the speaker. So I will just list a few problems I find interesting, but I don't work on them, or maybe tried to work on them some time ago and abandoned. And some of these questions I maybe spent 5 minutes thinking about. So the quality of what you're about to hear is not guaranteed. And as I was warned by Leon, I should not call these predictions, because predictions are very difficult. And I'm not going to do anything difficult. So I'm going to talk about, I'm going to pose some questions. And maybe some questions will need some preparations, and I will try to provide them. And there is no really structure in what I'm about to say, just a list of questions. OK, let me talk about, let me name the topics. What else? And maybe something else. OK, so well, this is some random list of topics which some of us find interesting. I should also, sorry. It's 5. This is 6. I'm not going to talk about 4. Well, sorry, I will talk about 4 beforehand. So the first topic is difficult, so I'll skip it for the moment. And I'll go directly to the second one. So it is really confusion in my head. How is it possible that Donaldson theory provides invariance of the smooth structure of 4 manifolds? And as physicists, we think that smooth structure has something to do with small scale structure, that you need to in order to be able to differentiate an infinite number of times, you have to know, how things look at the very small distances. Yet, as was shown many years ago by Witten, essentially the Donaldson variants essentially come, they're just particular correlation functions so these are correlation functions in a renormalizable quantum field theory. Well, this is maybe not the first quantum field theory you learned about in the textbooks. In textbooks, it's the n equals 2 supersymmetric Yang-Mills theory. Well, twisted, topologically twisted, but if you look at this theory, it's small at short distances. It doesn't matter whether it's twisted or not. It's really, the twisting really affects the global properties of the observables. And the most important part of this confusion is that the theory is renormalizable, which means that it actually doesn't matter how you define it at, so you should define it at some intermediate scale. I mean, you can imagine defining it on a lattice. And then, so you encode all the information about the theory in a set of couplings which you define at this scale, and then you run the energy flow and arrive at the infrared physics, which we know essentially captures the essence of Donaldson variance. And it seems strange that, I mean, you define it you define it on the lattice, so you forget about the really microscopic structure. So how is it that it knows about the smooth structure? So could it mean that the supersymmetric theories cannot be put on a lattice? Well, if yes, that's an interesting prediction from the, I would say, sophisticated math.
I think that's correct. You can put n equals 4 on a lattice.
Well, n equals 4 is a particular case of n equals 2. And you could also.
It's a different theory.
Well, I mean, what you could do is definitely you can formulate the self-duality equations on the lattice, and therefore you can set up, a cohomological field theory formalism, which would compute the integrals over the moduli spaces of lattice under self-dual gauge fields. So the thing is.
Besides the physics objection, there's a sort of geometrical point of view. I mean, Donaldson theory, you don't actually require smoothness. You can get by with much less. And a thing with a nice lattice like that, you know what I mean? You can't draw lattices different in scale in a very bad space, very bad topological space. It doesn't need to be smooth. Sullivan and Donaldson wrote a paper about how you can develop theory.
Right. So
it's manifold. So there's nothing wrong with, yeah. Then of course your lattices are all right. I think.
By Lipschitz is what they said.
Well, I'm not really satisfied with this. I mean,
that's not totally convincing. I've got it partially.
Yeah.
You can't draw nice pictures like that in really bad spaces. Kind of Michael Friedman plays with.
Right. So I think that there is some piece of knowledge which we are sort of missing by not thinking about these questions of what happens at the lattice scale in the gauge theory. And
You know, it also happens is even if you can put some subset of the equations on a lattice, the moduli space can look rather different.
right. So of course, I mean, the other answer which I often get is that the lattice version of cell duality equations don't approximate the actual cell duality equations. But what does it mean? That it means that our usual sort of lore that we put everything on a lattice and then take the limit when lattice spacing goes to 0, keeping the appropriate dependence of couplings on the lattice scale is actually wrong. So we need some other formalisms to deal with it.
You see the same problem also with the Zyber-Witten theory, with the spinners. Spin on the lattice exactly have some problems too.
But there, I think spin C structure is less problematic than the maybe.
Behavior of spinners.
Yes, I know. But I mean, the way okay, right. But I mean, physicists struggled with spinners on lattice for a long time, so that they sort of know some ways to deal with it, and partially they
Manifolds are not very smooth. It's very problematic, though. It's more problematic than Donaldson.
okay. So well, this is just some food for thought.
But from the side of topology, piecewise linear structures are equivalent to smooth structures.
But I guess when you say that from the point of view of topology, so what does it mean? So there is some equivalence relation which you impose, which is probably not the same equivalence relation which we would impose as physicists. See? So you assume some kind of I don't know, isotope equivalence or something. So you have some, how to say it? Physically, it's clear that that piecewise linear is not the same as smooth structure. So
It's smoothable.
it's smoothable. So physicists have other ways of regularizing theories at small scales. So we could add terms with higher derivatives to Lagrangian, or we could embed the theory into a finite theory as n equals 4. So it's actually funny that Mike mentioned that n equals 4 you put in the lattice, because in some sense we don't need to put n equals 4 in the lattice. Actually, n equals 4 being a finite theory, the only troubles it might suffer are infrared troubles, so that large scales. But
Because it's not asymptotically free, we know how to define asymptotically free theories in the continuum limit, but we don't know how to define the continuum limit n equals 4.
okay. So this is one set of ideas and things to think about. Now, the thing which in canonical quantum gravity. So people in canonical quantum gravity try to take basically Einstein equations, rewrite them in the Hamiltonian formalism. So assume some sort of foliation of the Lorentzian four-dimensional geometry by three-dimensional slices, and then formulate the initial value problem in terms of the metric and extrinsic curvature. So there is some canonical structure on this data. And well, the theory being generally covariant, there is no Hamiltonian. So essentially, all you need to do is to properly impose the constraints. And quantum mechanically, if you naively quantize this picture, you would say that you're interested in the wave functions, which will be the functionals of the three-dimensional matrix. Which should obey some constraints. And there are four types of constraints. So there are simple-looking constraints which say that if this is if this three-manifold is N3, then this function has to be diffeomorphism invariant. So that just says that your wave function is a function on the space of metrics modulo diffeomorphisms. But there is one more constraint, which is the so-called Hamiltonian constraint, which which reflects the invariance under the time parameterizations, or essentially the choice of the slice. And when you translate this constraint as a, when you try to write it as a differential operator, so this constraint is something horrible. So it has, it's a second order operator in the matrix with a complicated kernel, and it's very singular actually when you try to make it act on some reasonable functionals. So this is why, so this is at a technical level how most attempts to directly quantize the gravity without any additional structure fail. So I'm not going to solve this problem, of course. I just want to point out two things. That well, we know that gravity, as we observe it, is a perfectly sensible theory. So it's so when the energies of all processes which are involved are much smaller than the Planck energy, everything is fine. You have negligible corrections to the Einstein equations, and you can even describe all the effects of general relativity in terms of Feynman diagrams. As long as you are in this regime, you don't encounter any difficulties. So, so gravity looks like an effective theory with some kind of cutoff of the order of Planck scale. And so the difficulties which you see here in trying to define this operator in particular, which are short distance difficulties, in a sense, you're not even allowed to talk about them because they occur at the distances where the theory most likely is modified. So the question is, what is the formalism? Is there a formalism? For the canonical quantization of effective theories. What does it mean? Well, when we say that the space of states of gravity, let's say, is a space of functionals of the metric, this is an approximation. It is only valid when the metrics which we talk about here correspond to the slowly, well, they are sort of not very far from the flat metric or whatever is possible for the given manifold. So in other words, the Hilbert space, or maybe it's not even a Hilbert space, the space of states which we see at small energies. You see, so this is sits in a much bigger space, which is let's call it fundamental, which contains the degrees of freedom which we need to add to our theory at let's say at the Planck scale. Yet, for the questions of light scattering of sun, we don't need to know this whole structure. So the question is, I mean, this question can be also applied to other theories, not necessarily to the gravity, but this is just a famous example. How do we deal with the situation where we have we have a big space of states of which we know very little about, and some kind of relevant space, subspace of states, and we don't even know whether this is a Hilbert space or whether this is a Hilbert space, whether both are Hilbert spaces, now the situation where you have a space and a subspace, and we don't even, I mean, the dimensions are probably even not compatible, not comparable. Sorry, I mean, this one is probably much bigger than this one. To some extent, we encounter in condensed matter physics, where we, have a system of many degrees of freedom, like all electrons in the piece of metal, which have many states, of which we care only about a few: the band, the allowed, the states which electrons can occupy, the conducting electrons occupy. So maybe there is some analogy with condensed matter physics which could be used. Another remark which I want to make about this situation is that sometimes, if you're not interested in the full structure of in the precise solutions of this constraint, but you only want to enumerate the solutions, you might, instead of solving this horrible second-order differential equation, you might try to impose well, people who actually looked at these constraints know that in some sense they look like evolution operators. So this is an evolution in metric space. In one of the terms which was invented for this evolution is a multi-fingered time. So there is no time per se. So this time which we draw as we describe the slicing of the four manifold is becomes sort of irrelevant, because the Hamiltonian which generates evolution in that direction is 0. But somehow the constraints look like evolution equations in their own time. And as for any evolution equation, the solutions are described in the favorable situation by some initial values. So the question is, maybe you can find some surface inside the space of matrix model diffeomorphisms which such that the restriction of the wave function of the universe, so that's this wave function of the universe, onto the surface will determine it. And so what it means is that you would be studying not all three-dimensional metrics, but let's say metrics obeying some interesting equation. And that could be the constant curvature equation or something else. I don't know what's the what is the good analog? Sorry, what is a good slice there? Let me just give you an analogy. The analogy is not with gravity theory, but it's a theory which was called WZW4. So it was studied in the mid-90s by several groups of people, in particular by Losif, Moore, Shatashvili, and myself. And that's an attempt to find a 4D version of two-dimensional CFT. So kind of there are many nice things about the two-dimensional conformal field theories, and you cannot hope to generalize them directly to four dimensions because the conformal group at 4 dimensions is much poorer. But you might try to generalize some aspects of those theories, in particular the holomorphic factorization or the relation to the geometry of the modular space of bundles. So that theory, so WZW4 theory describes, so it's a kind of a sigma model. I mean, when you describe a set of fields, it's like the Skirm model, but Lagrangian is different. And so but it starts like a Skirm model. So you start with a 4-dimensional manifold, and your field is mapped from the manifold to the group. And the Lagrangian which you write, is essentially the energy of this map, to which you add a non-covariant term which is the integral over the product of the 4-manifold and, let's say, an interval or a circle. There are many different versions of a wedge product of a 2-form, which you pull back from the 4-manifold, times the canonical 3-form on the group, which is pulled back by the map. There are some relative coefficients which I will not write exactly.
So does X have a fixed background metric that you're using to?
Right. So X has a metric. So if X is a Riemannian manifold, so you use it here. This term does not use the metric, but it uses this 2-form. Now, well, as it stands, it's you might imagine it's one of the terms which is generated in the theory of pions in the background of some magnetic field, so omega could be a magnetic field. Now, in order for this term to be well defined, so this is a kind of anomalous term. In order for this to be defined, you immediately encounter the condition that omega actually has to be a 2-form with integral periods. So it actually has to be so it has to be closed, and its periods have to be integral, because this is an integral form, and so the exponential of Lagrangian will be well defined. It will be independent on the way you extend your fields into the 5th dimension if omega is integral. And the second condition is that, well, as it stands, it has a symmetry the global symmetry, where you just multiply the field G on the left and on the right by constant group elements. However, if there is some fine adjustment between this 2-form and the metric, the symmetry is enhanced. And so if the metric, in fact, is scalar, and omega is a scalar form, and therefore, actually, X4 is an algebraic surface if it is compact. Then you can multiply G by any holomorphic function on the left and any anti-holomorphic function on the right. So you get an enhancement of the symmetry. Again, unlike the 2-dimensional case where that symmetry is enough to completely solve the theory, just essentially
So G is always a complex Lie group in this.
No, the point is that, okay, it's an interesting, well, I don't want to get into this. So the Lagrangian is written for the maps into the compact group. But of course, at the level of, I mean, if you study the classical equations of motion, you can complexify, and then this will be on a symmetry. But even though, even if you don't, if you study the functional integral where G is compact valued, the fact that there is a symmetry is revealed in the following way, which actually I'm about to explain. So usually in physics, when you have symmetry, you have a corresponding currents, which you get by Noether theorem. So there is a current which corresponds to, let's say, to the multiplication by the holomorphic functions, which has this form. And there is the conjugate one. And so even though you don't have to consider this symmetry as it is, under the sign of an integral, you can perform the infinite Bessel transformations like that, and this will lead to the fact that on the equations of motion, these currents will be correspondingly holomorphic and anti-holomorphic. This is a 3 form, by the way. This is a 2-1, and this is 1-2 form on X. And so by analogy with two-dimensional case, what you can define here is the so-called conformal block. So you cannot compute. Okay, what I want to say is that this symmetry is not enough to completely solve the theory, but it is still sufficiently large to produce an infinite number of correlation functions, which you could in principle compute. And these are the correlation functions of these currents. So this is so there is some interesting current algebra in this theory. Now, why am I? Okay, so you can define the generating function of the correlators of these currents. Again, I'm really sloppy here. So suppose I'm only interested in the left currents, for example. Okay, now the beautiful thing about this correlation function is that it has a chance of being well defined, even though the theory itself, it's a non-renormalizable quantum field theory in 4 dimensions. So it actually, well, it is probably as bad as quantum gravity, maybe as good. One curious thing about this theory is that it is just as Einstein gravity, it is one loop finite. So Professor Karepin showed a long time ago that at one loop, right, on shell general relativity is finite. So I mean, trouble starts as 2 loop actually, and the same applies to this theory. When you can compute the one loop effective action, and it will have no divergences. Now, how can you solve? So how can you try to analyze this generating function? Well, it obeys 2 constraints. One constraint is the consequence of the fact that when you take the functional derivative of z with respect to a bar, you bring down j, the current. And the current is up to this multiplication by 2 form. It's something which we call the pure gauge. So it is a base. So if we contract j with omega, this solves this obvious equation. Okay. So that means that there is some kind of equation which I'm writing rather sloppily on z, which is the 2nd order, which it obeys. And that's the analog of the Hamiltonian constraint in general relativity. Now, there is another equation which is sort of the analog of this equation. So this is just the equation of motion. but it's also related to the variation of the Lagrangian with respect to the field G. So this equation up to anomalies which one can compute is actually it's a first order differential equation, and eventually it becomes the condition that Z transforms in a nice way under the complex gauge transformations. So what it means that this equation means that Z is a holomorphic section of a certain line bundle over the space of all gauge fields modular gauge transformations, over modular complexified gauge transformations. And the first equation says that it's of all possible sections, this is a kind of a special one. And together, I mean, if we'll just count the number of equations, these give you at most a finite dimensional space of solutions. So how do you analyze the space of solutions of this equation? Well, instead of solving this horrible constraint, you impose something like a Fourier dual. So let me call this the Hamiltonian constraint. So we just restrict our Z onto the space of A bars which solve the dual equation. So now we are in business, because now what we have, we want to study the space of connections, the 0-1 connections whose curvature is trivial, up to complexified gauge transformations. This is the modular space of instantons. And this equation means that Z is actually a section of some line bundle of a certain line bundle over the modular space of instantons. And so this is a finite dimensional space. And so this is what you might call the space of conformal blocks in four-dimensional theory. So you reduce the functional problem to a finite dimensional one by this trick. So you took this equation, and then you, instead of dealing with it directly, you restricted the function which you want to find on the transverse slice, the slice which is transverse to the evolution which this equation sort of generates. So I'm just suggesting that maybe one can find the analog of this constraint for general relativity. So since here is a curvature, and there we have a Ricci curvature, so maybe that the equation which I suggested was not so silly. OK. Done with that. The next question which I want to pose is the following. How unique is string theory? So we know, we all seen this picture, and I might have missed some corners. And we were all happy for some time that all physical string theories were found in some corners of this modular space. And that was an indication that string theory was on the right track, because it sort of eliminated additional choices. We all, as human beings, we hate make choices. So we like that somebody gave us the. Okay. Unfortunately.
It's your Eastern European background. You don't like to make choices.
I like to talk about not liking making choices. So that's Eastern European background. Okay, but what about so these are the so-called physical string theories, physical superstrings. Now tachyons, well, at least at this cusp points, stable solutions, reasonable perturbation theory, and moreover, we believe there is a non-perturbative completion. And it is this non-perturbative completion which actually makes this picture possible. That when you sum up all corrections starting at some corner, you might actually continue to another corner. What about topological strings? Well, mathematicians like, for example, A models. Well, you take any, let's say, Fano variety, and there is no bound on dimension. So here, the dimension, the naive dimension, doesn't go too high. You take any Fano variety, any sort of positive curvature Kähler manifold, the dimension can be as high as you like, and you can define, and in some cases even compute the free energy. Genus G, and it will be a function of an infinite number of couplings. So T alphas so the couplings are labeled by the homology of your target space, and there is an additional label which goes from 0 to infinity. And for convergence, you might also put a parameter Q, which is well, in a sense, it's just a bookkeeping device. In fact, Q can be shifted by change of these parameters T. Okay, so these seem to be well defined, albeit these are just the perturbative string amplitudes. So the question is whether the fact that we believe that string theory is unique means that these theories have no chance of being non-perturbatively defined. Or are we actually supposed to find them somewhere inside this modular space? And then the question is, when we see the target space of this A model, So this is the theory of Grove-Witten invariance. And we think that we talk about the space of some dimension which is very large. In fact, probably what the string amplitudes will perceive as dimension of space-time will be something completely different. Because in some sense, compared to the physical superstring, which has among the set of vertex operators fields which really propagate in let's say 11 dimensions or 10 dimensions at least. Here you only have indices. So here the vertex operators if you like, have functional degrees of freedom. Yes?
One immediate comment about your question is that, of course, the physical superstring has this quantum mechanical interpretation with the usual rules of probability, the S matrix, and so forth, and we're not requiring that for a topological string. And if you didn't require it up there, you would make get strings in any number of dimensions also.
Well, first of all, that might boil down that so if you want to have a unitary S matrix extracted out of topological string, you just impose some reality condition on these couplings.
Well, I mean,
vice versa, there you could just.
My point is the inter is an extremely strong condition that is implicit in dimension less than 11 and all these. If you relaxed it up there, you would get a much bigger class of theories.
But well, in a sense, the conditions which you mentioned sort of translate to the fact that, I mean, when you add all possible couplings to your, you consider all possible amplitudes, and in other words, add all possible couplings, you get something which is well defined. There are no divergences which are incurable, which you cannot, make sense of. And to that, at that level, these theories are as good or as bad.
You're perfectly fine. I mean, just they don't have to satisfy the condition that we put through physical superstring.
Well, okay, maybe.
Just a comment.
I don't know. Yes, maybe that's the way to approach it. But I would like to say that I would like to find another interpretation, another space-time interpretation of this theory. So I actually would like them to have a physical interpretation, but it could be that the seed space X at which we start is not the space in which the physics will be actually taking place. Because this set of couplings sort of corresponds to, if you compare it, to the set of couplings which you find for the physical string. So you have your Lorentz spins, spin indices, and then you have momenta, and the momenta are continuous, or at least you have many possibilities for them. Here, the only analog of momentum is this letter K, which is the gravitational descendant coupling. And it would seem that, in some sense, these theories are one-dimensional. So they have sort of 1 degree of freedom dressed with some discrete degrees of freedom coming from cohomology of your target space. But where is this one-dimensional space inside the M-theory land? It's an interesting question. OK. Now, continuing on this.
Limit of this below.
So you see, you can always. So there is a quantum field theory. There is no limit. These couplings can be derived from a field theory. So you don't actually, even though in this picture they defined using strings, Riemann surfaces, or some structure. There is a functional which can write on the space of these couplings, for which this genus G amplitudes will come as will be obtained from Feynman rules. So this is really G loops in a particular quantum field theory. Although this quantum field theory is sort of interesting in the sense that it has vertices, it has some effective vertices which come from the integrals of the over the moduli space of genus G Riemann surfaces of the so-called Hodge classes. And these look like actually the effective vertices for some yet more fundamental theory from which this is obtained by integrating out massive degrees of freedom. So there is something even more elementary. So even if you think about that topological strings are elementary, they're actually not. There is something even more elementary which nobody knows what it is. So there is some substructure there which mathematicians should be able to uncover if they think about this in the proper way. But I want to pose another question. Now that I've spoke about the A model a little bit, which can be loosely called target space quantum gravity. It's sort of, well, it's not in the list, unfortunately, but I just remembered about it. So the conventional A model which studies, roughly speaking, the holomorphic maps of the two-dimensional wall sheet into the target space, actually is attached to a symplectic geometry. So X is symplectic, and this holomorphistic condition is defined using a choice of an almost complex structure, and you can actually vary it. And so it should be independent. So the model is independent these are J holomorphic. However, when we write Lagrangian, which sort of enforces this condition, there is a simple way of modifying it so as to make it, so as to introduce the sort of, so the choice of the complex structure in target space together with the choice of a symplectic structure is the choice of a metric. So when we say that the model is independent of the choice of complex structure, it sort of means that from the target space point of view, this theory is semi-topological. So it knows something about the metric, but it doesn't care about most of it, or half of it, depending on how you count it. But now we can introduce the superpartners, J, and modify the Lagrangian some kind of supercurrent, so that now it actually will be a little bit sensitive to the choice of a complex structure in target space. And in fact, these FGs now will define closed differential forms on the space of complex structures modulo diffeomorphisms. So that the standard A model corresponds to taking the degree 0 differential forms. So closed forms of degree 0 are just constants. So that's why. So this is why you get the in the standard formulation of the A model, you get invariants. So they're independent of the complex structure. But in the modern philosophy, the invariant is just the degree 0 term in some complex. And so so we should think in terms of target space. Grown with invariants. So these are the cohomology of the complex of some compactification of the modular space of complex structure of your target space, in particular for a Calabi-Yau. So these are the interesting modular spaces. And by mirror symmetry, this is something which I don't know even how to approach. If you start with a B model, which is defined using the complex structure in target space, is supposed to be independent of the Kähler structure, you should be able to also extend it and make it into a family of models over the modular space of Kähler structures. Now, if your manifold X is actually two-dimensional, then this modular space of complex structures is the Deligne-Mumford compactification space. And so if you start with the A model for which the target space is a Riemann surface, when you sum it all up and now extend to this family, then you get a new string theory. This is this old Michael Green's philosophy that when you study string theories with two-dimensional target spaces, these define for you new bullshit theories for new theories. And in principle, you could iterate. So, OK, so well, 3 out of 6 is probably not a bad. Yes.
I was going to see what people think. Since this is very interesting, and rather than rush through the rest, since we have you here, why don't we have another talk another week? And we can do the other half.
Well, I hope it was not too boring, because I don't know, it's people were sort of sleeping.
Scheduled for next week, Claude's going to talk, but the week after is open, and I've been struggling looking for someone, so maybe we found it.
No, I cannot. Sorry. I can start in 50 on the 15th. I can. OK. Well, I hope that integrability will become an important condition at some.